Okay. So
perfect timing.
let's thank the speaker again. Our next speaker is Jamie Vicary on categorical formulation of C-star algebras.
I'm just going to get
You misspelled Reykjavik to Vicary.
Are there 5 Gene Vicaries at Imperial? You got this one.
It's 2005 must be.
Yeah.
I put in the
hello. My name is Jamie Vicary 05. I'm going to talk about C-star algebras and how they fit into this categorical framework for quantum mechanics that we've seen a little bit of this afternoon. Okay, so first of all, why do we care about C-star algebras? I'm going to devote most of the talk to actually showing how the proof works. So I'll just do this very quickly, but it's clear that there are lots of reasons why we care about C-star algebras. They've already been mentioned in Alex's talk already this afternoon. They come up all over the place. You can't do quantum mechanics without at some point running into C-star algebras or encountering them somehow. The foundations of all these sort of 3 things that I've listed here, if you want to think about it like that. And I suppose fundamentally it comes down to the fact that if you have a quantum system and its algebra of observables is a C-star algebra, so you can't get away from these algebraic structures. And it's not just in what do I have to point this at to make it work?
You're right.
So
Be careful.
okay.
Yes, it's very.
Okay. It's not just finite-dimensional quantum mechanics, of course, and like some quantum information theory style quantum mechanics, also quantum field theory, and there are lots of problems, fundamental problems at the bottom of the foundations of quantum field theory, and people try and solve these problems by using C-star algebraic techniques. So it's all pretty powerful. Okay, but what is a C-star algebra anyway? So there have been lots of ways to think about C-star algebras suggested over the years. The first time people ever came up with C-star algebras was because they came up with Hilbert spaces, and then they looked at all of the operators, all the bounded operators from a Hilbert space to itself, and then realised that this was kind of a nice algebra. So they called this C-star algebras, just the algebras that you get by looking at operators on Hilbert space. So that's just this sort of in the wild definition, if you like, these sort of things that we come across naturally when we've got Hilbert space. But then it was proved that actually you can have a much nicer abstract definition, which just says it's a complex algebra with some anti-linear involution that satisfies that property, and also a norm. The norm is a really important thing. The norm is what gives C-star algebras all their amazing properties. It's got to satisfy those things. It's called the C-star conditions. And that was great. That was discovered, I think, in the 50s. And I suppose the elegance of this algebraic characterization is one of the reasons why it's so powerful. Okay, so what effectively we're going to do in this talk is give it a new definition that's sort of completely different in style. First of all, we're not going to talk about norms at all. We know norms everywhere, at least not obviously. They're all going to be equivalent, so they're hidden there somewhere. But obviously there's going to be no norms at all. The basic thing we're going to do is, instead of working over a complex vector space, we're going to work over a complex Hilbert space. So instead of saying that our vector space has a norm, which you require for a conventional C-star algebra, we're going to say that our vector space has got an inner product that in fact makes it into a Hilbert space. That's going to be the sort of key difference. And this approach seems to work very well. And you can prove it's got lots of nice properties. But the one problem is that it only works with finite-dimensional C-star algebras. Now that's only a problem if you want to use infinite dimensional C-star algebras. And I can talk at the end about why that is and what we might want to, anything else we might want to say about that. Okay, so what's the point of this new definition? Well, first of all, it's phrased in a categorical way. And if you like category theory, that's great, and it gives you a lot of flexibility to do things in a different sort of way. It gives you a new perspective on finite dimensional C-star algebras. Some things that conventionally were a bit mysterious, perhaps, or difficult to prove about C-star algebras become easier, at least, to prove in this framework, and vice versa. There are some things that are conventionally easier to prove than more complicated to prove in this framework, but it just gives you a new perspective. And because it's categorical, you can immediately vastly generalise what you mean by C-star algebra, because what we're going to come up with is we're going to say, you just draw these pictures, and these pictures are a C-star algebra. And if you take a model of these pictures in Hilbert spaces, then you've got conventional C-star algebra. And if you've got some other category lying around, you can find a model for these pictures in that category as well. And then you kind of have a right to call that a generalised or exotic C-star algebra if you really want to. And then maybe if this new category was a toy model for quantum mechanics, or perhaps a model for something that might go beyond quantum mechanics, then you can really start to study what new or different or interesting properties your C-star algebra might have in that setting. And there are lots of applications of physics, but I suppose I won't emphasise those today. Okay, so we need a new way to look at what algebras are. What is an algebra anyway? Well, it's a vector space. I'm just going to concentrate on complex vector spaces. Everything that I say in this talk is just, at least for the main body of the talk, is going to focus on complex Hilbert spaces. So you can do a lot of this much more generally, and if you have a look at my abstract, I do it more generally, not necessarily working with Hilbert spaces, but just for the purpose of this talk, just assume that everything's a Hilbert space. Okay, but first of all, so what is a complex algebra? It's a vector space with a multiplication map that goes from V tensor V to V, and a unit map which goes from the base field to V, which just picks out an element of V, or a unit element of the algebra. And it's got to satisfy an associativity equation and unit equations, and we're going to draw pictures of these rather than drawing them out in the usual algebraic way, which I think makes them much easier to understand what's going on. So what this associativity equation says, how you read that, is you say, well, you start with 3 copies of V. All of these vertical lines are copies of our underlying vector space V. So we start with 3 copies of V. We multiply the first 2 with each other. So that's what this funny vertex here is. It's just my multiplication map M. And now I'm left with 2 copies of V. And I'm going to multiply those together using my multiplication map M. And I end up with a map that starts from having 3 copies of V and ends up with just having 1 copy of V. And I can also sort of do that the obvious other way. And this is just my associativity equation. So normally when you state associativity, you have to do it, say, in terms for all triples of elements A, B, C in my vector space, this holds. This is a really nice element-free way of denoting the same law. And it's great, you can draw a picture of it as well, which makes it a lot easier to work with. And these are my left and right unit equations, so that these sort of work in a similar way. The new thing here is this little object here. This represents my unit element, U. So this just says, if I have a unit element and some pre-existing element of my vector space, when I multiply them together, I just get the identity. Nothing happening. So that's it, and I can do it on the left and the right. Okay. But what if my vector space V is actually a Hilbert space? If you have a Hilbert space, and you have linear maps from Hilbert spaces, this lets you take the adjoint of any map. So if a bounded linear map, I should say. So if we have a bounded map from some Hilbert space A to Hilbert space B, we can take its adjoint, which is the map backwards, going from B to A. And this is going to be really important. And this has come up already this afternoon, so I don't need to talk about it too much. But the way we draw that is just by flipping diagrams. So if you've got some diagram here that represents the composition of some linear maps, and if they're actually linear maps from Hilbert spaces, we can apply the adjoint to everything, and we draw that just by flipping everything. So we started with a multiplication like this that went from V tensor V to V. Its adjoint, and dagger, is going to go from V to V tensor V, so it's going to go backwards. And similarly, we're going to, instead of a unit, we're going to have a co-unit, which is the adjoint map, that goes backwards from V to C. And these will satisfy just the adjoint of these equations, everything flipped upside down. Right. Okay. So that's what an algebra is, and if our algebra is in fact over a Hilbert space, we can also draw our diagrams upside down. Okay, so what's a dagger-Frobenius algebra? Well, a dagger-Frobenius algebra is a property that an algebra on a Hilbert space might have. So if we've got an algebra on a Hilbert space, it's an algebra, so we've got multiplication. It's on a Hilbert space, so we can take the adjoint of the multiplication. And then we can ask that these things fit together in a nice way. And this thing here, this is the Frobenius identity. So this says that if we start with 2 copies of our vector space V, then if we apply the co-multiplication here, so we go from V to V tensor V here, then temporarily here we've got 3 copies of our vector space V. And then we're going to multiply these second 2 together, and then we end up just with 2 copies of our vector space again. So overall we've got a map from V tensor V to V tensor V. That must be the same as doing this, first multiplying and then co-multiplying. This must be the same as sort of the mirror image of the first thing. These are the Frobenius equations. They look sort of weird, but actually they're very natural, they crop up all over the place. So if we've got an algebra on a Hilbert space that satisfies these equations, we call it a dagger-Frobenius algebra. Okay, so why do we like dagger-Frobenius algebras? Why should these have anything to do with C-star algebras? Well, the reason really boils down to this observation due to Bob and Dushko and me. It sort of goes like this. So, take any complex algebra on some vector space, the sort of thing we've been talking about, and choose any element alpha, then we can always find some operator which is the right action of alpha. So we start with V, and we end up with V, so it's a linear map from V to itself, which just multiplies on the right by our chosen element alpha. That's the right action, that's kind of a standard thing. Okay, but we're always working in a Hilbert space, so we can take the adjoint of everything. And so we know how to take the adjoint of this picture, we just flip it upside down, and we get this. And then we might ask, this new operator that we've got, the adjoint of our right action, is that also the right action of some other totally different element? It's not obviously the right action, because this isn't of the form multiplied by something, which this was. This is of the form co-multiplied by something, which is totally different. Okay, so this is the question we're asking. Is it also the right action of some element? And the answer is yes. Turns out, if we're working with a dagger-Frobenius algebra, you can show this quite easily. So this is the adjoint of our right action. And we can stick in here a little unit element. So all we're going to do is stick a unit element on there, and the unit axiom said we can just stick these unit elements anywhere we like. So that's great, so we just do that. And now we see that here, we've got this down, up, down pattern. But the Frobenius algebra axioms told us we can always replace this with down, up, down the other way. So we've got a down, up, down there, and we're going to replace it with an up, down, up. That's all we've done there. But now we're just going to squish this a little bit. We're going to move this part of the diagram, we're going to squish it down to there. And now we see that we've massaged it into the form of taking a right action. But the thing we're taking a right action of is this sort of weird thing here. But anyway, we've shown that our alpha dagger is the right action of this thing that we're going to define as alpha prime, which is this weird sort of thing that's derived from alpha, but seems a bit complicated. Okay, so we've shown that for any alpha we can define an alpha prime such that R of alpha dagger is R of alpha prime. So let's think about this map that sends alpha to alpha prime and try and understand its properties. So first thing we can try is doing it twice. So what's the prime of alpha prime? So well, we know how it's defined, so we just draw it out like this. And then we notice that after we just use the definitions, we get this picture. And then we can use our Frobenius laws again. Here, we've got this down, up, down pattern. We replace that with an up, down, up pattern from the Frobenius laws. And then we see here, we've just got a unit dangling off. And by the unit law, that's just the identity. Here we've got a unit dangling off. And by the unit law, that's just the identity. So overall, these just can be taken away. And we just get that with alpha again. So Key will be excited because we've got an involution. Okay? So alpha to alpha prime is an involution. Do it twice to get back to the same thing. So going back to our observation that it takes the way it interacts with taking right adjoints, we can see that in fact this embedding takes any element of the algebra and gives us the right action of that element. In fact, this is involution preserving because we've got an involution on our algebra elements, alpha to alpha prime. We've got an involution on our right action. We've got an involution on operators on the vector space by taking adjoints. And because of this relationship, this embedding must be evolution preserving. So that's sort of quite handy. So this just summarises the stuff that I just said. This is what we've discovered. Every dagger-Frobenius algebra admits this involution, alpha to alpha prime. This makes it into a star algebra, because that's what a star algebra is. It's just an algebra that's got some antilinear involution associated with it. It doesn't necessarily have to satisfy any particular other properties at the moment. And we've shown that there's an involution-preserving embedding by taking right adjoints into the algebra of operators. But the first definition of C-star algebra that I gave was that a C-star algebra, as it was first conceived, is just defined to be the algebra of operators on a Hilbert space. But these right adjoints, these are exactly operators on a Hilbert space. And it kind of follows sort of obviously, if you look at the axioms for a C-star algebra, that if you have any C-star algebra, and you find any sub-algebra of your C-star algebra that's closed under taking stars of elements, so a sub-star algebra, this is obviously also a C-star algebra. So you say, well, how do you show that? You need this sub-star algebra, has to have a norm and everything, blah, 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 make it into a C-star algebra. Well, because this sub-star algebra is embedded into a C-star algebra, you can just steal the norm from the bigger space. You say, what's the norm? Let's just steal it from the C-star algebra I'm embedded into. And that works fine. So this gives us the result that really is the reason why that C-star algebras are so nice. Every dagger-Frobenius algebra admits an involution. This map alpha goes to alpha prime. And because of this involution, we know that it embeds into the algebra of operators on the Hilbert space. But that's just a C-star algebra, so we can steal the norm from there and turn our dagger-Frobenius algebra into a C-star algebra. So that's great. So every dagger-Frobenius algebra is also a C-star algebra, finite-dimensional C-star algebra. But we could make this sort of nicer, maybe, because there will be loads of dagger-Frobenius algebras that will give us the same C-star algebra. So it's like we're not really comparing like with like completely. So we might say, okay, are there some sort of special properties that we can ask that our dagger-Frobenius algebras have to have in order to establish a sort of one-to-one correspondence? And okay, so I'm doing all right for time, I think. So what we're going to do is we're going to try and find some new things that we can say and give us a new theorem that will actually have a sort of one-to-one correspondence. So we'll obtain special types of dagger-Frobenius algebras, and of course they will be C-star algebras by this theorem. But also we'll show that every finite-dimensional C-star algebra can be turned into one of these special types of dagger-Frobenius algebras. So there'll really be a one-to-one correspondence. Okay, so we need two extra properties. So I'm going to look at one on each slide. So we've seen that we can get this antilinear involution, which I call prime. This was kind of an important thing. This is an antilinear map, and it goes from the Hilbert space to itself. But because it's a Hilbert space, we've also got this canonical way, this canonical antilinear map from the Hilbert space to its dual space, just by taking the inner product. We can compose these. We've got an antilinear map from V to V. We've got an antilinear map from V to V star. We can compose them, and the antilinearity goes away. We have a linear map from V to V star. So this is quite interesting. So for any dagger-Frobenius algebra, we've got this canonical linear map from the underlying Hilbert space to its dual space. And this somehow encodes this prime involution. So I like calling it the linear involution, as distinguished from this sort of antilinear involution that we started with. And if you're doing category theory, this is great, because typically, category theoretically, you work with categories that have morphisms given by the linear maps. Antilinear maps are kind of a pain to work with, because you don't have to stick them in your category, you don't really know how to talk about them. But if you've got this, if we've translated our involution into a linear map, we can talk about that more easily, so that's quite sort of fun from a category theory perspective. But of course, if V is a Hilbert space, V star is a Hilbert space, so this is a linear map between Hilbert spaces, and we can ask if this is unitary or not. For some dagger-Frobenius algebras it will be, for some dagger-Frobenius algebras it won't be. And if it's unitary, then we say that the dagger-Frobenius algebra is unitary. We're going to define this to be a property of dagger-Frobenius algebras. And if you know about Frobenius algebras, you might know that conventionally people talk about Frobenius algebras being symmetric, which isn't commutative, it's something weaker. And it turns out this unitarity property is just this standard symmetric property that people use to Frobenius algebras.
Is this related to the fact that if you had started with a left action instead of a right action, you would get a different anti-union solution, which
Yes,
probably have been...
exactly. So if a dagger-Frobenius algebra is unitary if and only if it's symmetric. It's also unitary if and only if the left, doing it on the left, doing it on the right, give you exactly the same answers. Okay, and so that's my unitary property. There's one more property which is my specialness property, and this is very standard property for Frobenius algebras. So that if you start with your vector space, and then you co-multiply to get v tends to v, and then you multiply again to just get back to v, that's just like doing nothing, that's just the identity, that's being special. Okay, so now we can state what the main result is. If we have a star algebra on a finite-dimensional complex vector space, then we can say, can we make this into a C-star algebra? If so, it means we can find a norm that makes a C-star algebra. But another property might be that this complex vector space will admit an inner product. And then because it's an inner product, we've got our multiplication in our unit, we can expect a co-multiplication in the co-unit, we can then see if it's special, if that's a property, we can see if it's unitary. And it turns out that these properties are equivalent. It will admit a norm, make it a C-star algebra in a conventional way, if and only if it also admits an inner product. It makes it into a special unitary dagger-Frobenius algebra that we've just described. And it's well known that if it admits a norm, the star algebra to C-star algebra, then that norm is unique. And so the whole point about this theorem, this is because of these special unitary properties here, this is also true for this inner product. If it admits an inner product, making the algebra into one of these, then that's the only inner product. Good job. So it's kind of so that was what was so nice about the norm of the C-star algebra. So it's nice that we've managed to retain that feature. But there's something to be pointed out here. If you're used to playing with vector spaces and norms and inner products and things, then you'll know that there's a canonical way to take any inner product and turn it into a norm. Sometimes vice versa, if you've got a norm, you can turn it into an inner product. But that's not what's going on here. This norm and this inner product, for these equivalent properties, aren't related in that way. So you shouldn't think of it like that. It's something sort of more fiddly. And it's just worth reiterating, this doesn't work for infinite-dimensional star algebras. But the simplest reason it doesn't work is that there aren't any infinite-dimensional Frobenius algebras. All Frobenius algebras are finite-dimensional. And the easiest way to prove that is you can easily show that if you've got a Frobenius algebra on a complex vector space, then that complex vector space is isomorphic to its dual. But it's also well known that any infinite-dimensional complex vector space is strictly smaller than its dual. So there's no way that you can have a Frobenius algebra on an infinite-dimensional vector space. So that's all I wanted to say, really. I've got a bit of time, so I can just spend one slide sort of explaining how this works. How do we go the other way? If we have a C-star algebra, how do we turn it into a dagger-Frobenius algebra? In particular, one of these special unitary dagger-Frobenius algebras. How do we find this inner product on the vector space that gives us these properties? Well, we just use this well-known fact that every finite-dimensional C-star algebra is just isomorphic with a direct sum of matrix algebras. So we can just imagine we're dealing with a matrix algebra. Makes things easier. But every matrix algebra has got this sort of canonical inner product, just by taking, for two matrices, alpha and beta, just take the trace of alpha dagger followed by beta. And in fact, if you do this trick by, so this would define, without this n here, it would define the inner product. We can also just scale this n here, which is the dimension of the matrix algebra. So the square root of the dimension of the matrix algebra. And this will give us another inner product. And it turns out that this will in fact be special and unitary. And you might think, well, hey, why is this dagger-Frobenius algebra? We just started with the matrix algebra. Well, if you know category theory, then you'll look at these diagrams and it'll clear. If not, then it probably won't. Okay, so I think that's all I've got time to say about that. So the point of this slide is just to make the point that the axioms for a special unitary dagger-Frobenius algebra are completely geometrical. They're completely not wedded to the fact that our underlying field is the complex numbers, that we can do functional analysis, all of this stuff. It's a completely different way to describe things. The axioms are just pictures, which is completely not the case for the axioms for conventional C-star, the conventional axioms for C-star algebra. So like I sort of said at the beginning, if we've got enough structure in our category, in particular if we have a monoidal dagger category with duals, which is a technical thing, then we can formulate this requirement of being special and being unitary, and then we can sort of explore exotic C-star algebras in these settings if we want to. Okay, so I think I'll just skip over that. And this gives us a way to study quantum logic and algebras and observables in any sort of exotic setting that we're interested in. So that's kind of a good thing. And it's also relevant to physics, so if you've ever heard of topological quantum field theory, you might have heard them mentioned in the same sentence as Frobenius algebras, and this stuff is all very related. Okay, so that's it.
Other questions, comments?
Yeah, I would make a comment. It was on your slide, but you sort of squeezed over the fact that the commutative case of this dagger-Frobenius algebra exactly corresponds to basis.
Yeah.
Gives actually what this theorem then says is that in a way C-star algebras are non-commutative bases. So
yeah, so I didn't really mention that, so that's a nice theorem that if you have a commutative dagger-Frobenius algebra in the category of Hilbert spaces, it follows from this, in fact it follows from much less than this, that that's just a commutative C-star algebra, and it's one of the commutative C-star algebras are just algebras of functions, points. So in fact a commutative dagger-Frobenius algebra is just completely defines and is defined by a choice of orthogonal basis for the underlying Hilbert space.
So, this is the question, but so what's the role of things like GNS and stuff like that? Because now you kind of, your axioms almost presupposing something like
I don't think I'm... well, I mean, it's a completely different perspective. Certainly, it's not obvious. If you take the conventional definition of the C-star algebra, it's not obvious that every C-star algebra embeds the algebra operator in its Hilbert space. That was why these two definitions was known that they're equivalent for the time. And from this perspective, it is much more obvious. Sure, but there are other properties of C-star algebras that are much less obvious. That's kind of the thing I said at the beginning about how it's just a different perspective, and some things are more obvious, some things are less obvious. But I'm certainly not assuming anything very powerful. I'm not assuming any sort of deep function analysis, mumbo jumbo, or it's just some pictures. Sorry.
Okay, so can you say a few words about how many you managed to do it for various dimensions?
Well, I mean, so obviously you can't, because there aren't any infinite-dimensional Frobenius algebras, so you could just sort of stop there and give up. I wish I had something more intelligent to say about that, really. I mean, if this is at all a deep or fundamental way to formulate C-star algebras, given how important infinite-dimensional C-star algebras are, especially in physics, it would be great if there was some analogue. But I think it's going to need to be somehow deeply more sophisticated to take it to get over this obvious stumbling block. I don't know. I've got no idea how you would do
I got confused. You said every dagger-Frobenius algebra that's unitary is symmetric, but then if it's commutative, then it basically becomes an algebra of functions. So I know what commutative means, but what did you mean by symmetric? I thought.
Okay, yeah. So symmetric is the same as commutative. I think so. It's a stupid term. I don't think I've got a picture of it. So a Frobenius algebra is symmetric in multiplying and then doing the co-unit. So taking the co-parent, so multiplying and then taking the co-unit is the same as switching and then multiplying and then taking the co-unit. So if we didn't take the co-unit at the top, that would just be the commutativity law. But because we're putting this co-unit at the top, it makes it strictly weaker.
So symmetric is weaker.
I just want to make a remark following up on this question on infinite-dimensional situation. So some years ago, Samson, Rick, and I invented these things called nuclear ideal systems, which were precisely meant to handle a number of infinite-dimensional phenomena where essentially things became too singular to work properly. And it might be an approach to doing some of these things. Of course, in the end, sometimes functional analysis mumbo-jumbo will probably happen because we'll probably be using some kind of approximation.
Sort of unfortunately, I use this, crucially, this incredibly powerful theorem that says every finite-dimensional C-star algebra is just a direct sum of matrix algebras. And this is just completely not true for infinite-dimensional C-star algebras.
Right.
There will be a class of them that will kind of look like infinite-dimensional matrix algebras in this sense. And they'll just be lots of others that are just nothing like that. And so I don't know how...
Is there any kind of approximation regarding?
No. But there's a class of them as well that's like that, and they're actually called approximately finite-dimensional ones. Which means not finite-dimensional enough, not finite-dimensional, but they're nice, as nice as finite-dimensional ones.
They're not good enough to do quantum mechanics?
No. I don't. Maybe I'm going to know more.
AF algebras are, well, they're well understood, but you need a larger class. You want symmetries and super selection rules in quantum mechanics, and you simply need more structure. If I may make a comment, it seems to me, well, since you're using Hilbert space and using all the structure there, you of course have a normed vector space you start from, and then my guess is that you use the fact that in finite dimensions all norms are equivalent. So this need not necessarily be the right C-star norm, but since you have
C-star norm would be unique if it exists. So
yes, but that doesn't matter in finite dimensions because all norms are equivalent anyway, so you can use any norm. And taking Hilbert space, you have a norm.
Right.
And this is also something that, of course, would not be true in infinite dimensions.
Yes.
Yeah. Okay, so... Oh, yes.
So first of all, actually a comment on your last comment. It's certainly true that norms are equivalent in finite dimensions if the questions you're asking are questions of convergence. But there are other sorts of geometric questions one can ask, which of course will be important. My question is, can you say anything, perhaps by adding extra structure, in the direction of characterizing finite-dimensional group algebras?
Right.
It's an explain group C-star algebras, for say for finite groups.
So, what sort of conjecture, what sort of thing would that look like?
Well, I mean,
every group algebra is just...
So suppose that you're given the group as data, and you're given a Frobenius algebra, and maybe there's some sort of a representation. Can you characterize the situation in which the representation you're looking at is the regular representation with that stipulation?
There are certainly nice things to say about representations of finite groups and things and how that sort of fits in. I don't know how that really is the question. Maybe we could talk about it afterwards.
I think we will cut the discussion short here. Thanks, Vicary, again.
Starting to get a lot more useful.